Great. Good afternoon, everyone. Thank you for joining our session. I hope you are having a great time at the event in terms of networking, learning, and really providing your valuable feedback. Welcome to our session, how Trellix adopted Amazon OpenSearch in terms of cost as well as the value that they have earned from this service. Amazon OpenSearch is a comprehensive tool, enables you to perform the various search use cases. And it stands at the forefront of search and analytics, innovation. And it's not just a kind of search engine where it's a comprehensive tool to kind of really enable you how you think of revolutionizing how you interact with the data as well. And OpenSearch is really kind of trying to push the boundaries in terms of the advanced analytic search capabilities, starting from semantic search all the way towards your hybrid search models as well. So the true magic of OpenSearch technology really relies on how you transform your business in terms of solving the real-world problem. I'm Kanniah Vijay, a senior solution architect aligned with UK ISV segment, and I'm pretty much with AWS close to 5 years. And my day-to-day work is pretty much helping customers to scale and adopt various AWS services. Today, I'll be co-presenting with Pat Lynch from Trellix to talk about their journey. So let's begin. So the session's agenda is designed to cover some of the fundamentals of OpenSearch. So the first part where I talk about OpenSearch use cases and some of the integration and innovation types, as well as some of the key offering for you to adopt your various search use cases. And then we'll delve into some of the ingestion pipeline and OR1 instances specifically designed for OpenSearch workloads. And we talk about some of the integration use cases and leveraging some advanced ML-powered search capabilities as well. The second part is going to be more of Trellix trying to give their perspective on how they have started leveraging Amazon OpenSearch, moving from Elasticsearch in terms of migration and adopting various other features over a period of time, starting from POC all towards your production deployment. And I want you to kind of do a mind mapping of the first part of the session where we cover about the OpenSearch fundamentals to correlate with Trellix adoption in terms of the various challenges that they have seen and how they have improvised their overall solution to adopt the scale and also to reduce their cost of their service as well as they migrated. For audience who are pretty much new to OpenSearch, OpenSearch broadly supports three main use cases. It's search, where it offers you a full text search, pretty much allowing you to deal with any type of data types, including structured data, document, unstructured data. And it provides advanced features like relevancy ranking, faceting, and some of the application-related use cases like product search in e-commerce world, and some of the content management system-related search as well, and some of the enterprise-wide search capabilities. And the second use case is about analytics, where it offers you more powerful log analytics, allowing businesses to monitor their application performance along with the enhanced deep security threat detection capabilities in terms of identifying vulnerabilities in terms of the application and threats. And it also allows application monitoring capability to support data ingestion in terms of volume and also performing ad hoc analysis of various search capabilities in terms of the huge volume of data. So we are talking about petabyte of data. And the third use case is pretty much covering vector and Gen AI workloads. So this is where you will see use cases like vector search and similarity search performing, enabling AI-powered applications where it can effectively store and analyze your high-dimensional vectors where you're trying to convert your input text into corpus of vectors to allow you to find the semantic meaning across your various search use cases. And typically, the use cases would be the recommendation systems and natural language tasks. And when you combine OpenSearch with your generative AI workloads, eventually you will see the enhanced search results powering conversational AI search and enabling semantic search capabilities across the various data types. So depending on your use cases, you can use OpenSearch aligning with these workloads, and pretty much you see OpenSearch has been evolving for many of the GenAI workloads in terms of semantic search and advanced ML power search capabilities. So just let's do a quick level set on what is OpenSearch. OpenSearch is a fully open source search and analytics engine powering Amazon OpenSearch Service. And it is an Apache 2.0 licensed, open source licensed offering along with its community-driven project as well. And OpenSearch have reached a major milestone in Q3 2021 by joining the Linux Foundation to be the open source community offering project. And organizations across many industries have really embraced OpenSearch. The reason being it has been close to more than 750 million downloads since its inception. And then we also seen ranked within the top 4 search engines. And we also seen 80+ partner adoptions, and they are eventually growing this community-driven project. And hundreds of new features with examples of hundreds of weekly community contribution as well. And last but not the least, support or adoption of multiple service provider, including AWS, Oracle, Azure, and GCP. So this gives you a perspective of how OpenSearch is impacting various industries and the service adoption of various service provider as well. So how do customers get started in leveraging OpenSearch on AWS? Again, so one of the approach, so the 3 possible approaches you can get started with. The first approach is using self-managed deployment model. So what that means is OpenSearch can be hosted on an EC2, on an EKS, or an AWS Outpost as well, providing a full control of your installation, configuration, and management of the entire solution. So wherever you see there is a need for you to manage the entire workload with all full configuration and flexibility, then I think that's where you would leverage the first option of self-managed approach. And the downfall of this approach is that you need to have an hands-on management and expertise to really manage the cluster. So it brings the additional complexity of your operational team so busy in dealing with managing the clusters, the scalability, and all other aspects. The approach 2 is leveraging Amazon OpenSearch Service, a fully managed service that enables you to completely eliminate the challenges around provisioning, setup, maintenance of your OpenSearch clusters. And again, it offers you a full ease of scalability, high availability, resiliency, security, and again, the integration possibility with broadly all other AWS services. The approach 3 is using Amazon OpenSearch Serverless. This offering allows you to really use the offering without need you to provision any servers or managing those servers. And again, the minimal knowledge required for you to get started with OpenSearch is through serverless approach. Pretty much easy to get started. And we'll talk about the architecture of how serverless is different than the provision clusters. The easy way to get started is a 3-step process. Step 1, where you start injecting the data into OpenSearch, and step 2, where the data get indexed based on your data set in terms of application logs or your framework-related logs, or even your data logs in terms of the data lake that you may have. So based on those analysis, where the data gets indexed automatically. And step 3 is where you start, based on your indexing strategy and the way you want to leverage this data by various search queries, where you perform those search using your thread patterns or the query patterns on OpenSearch. So let's have a quick look at some of the basic fundamental search types. To start with, lexical search. And lexical search refers to a process of where you're searching for a keyword or a text within the corpus of data. And the other name for lexical search, typically you would hear full text search or a keyword search, all remains the same. And as you can see in the example where a user performs a search on Amazon, and it's an 8-foot blue couch. And behind the scene, there is an analysis process of where the query is broken into individual terms. So this is eventually it breaks into 4 different terms, and those terms are matched against your corpus of document. And then behind the scene, again, there is a scoring mechanism happens where a score is associated with all of these different terms, and based on the score, where the results are returned to the user. And under the hood, lexical search uses BM25 algorithm to calculate the document relevancy score based on which the results are provided. And typically, you will see lexical search are pretty much good in terms of precision, where precision is a critical aspect of your relevancy score. Then lexical search is the best approach to get started. And typically, you will see in the e-commerce use cases as well as the legal document retrieval, where precision is important in terms of the keywords that you're looking for. Another type of search is a semantic search. Semantic search again refers to an ML-powered advanced search where it tries to understand the context and the meaning or the intent of your search. And as you can see in the example where a user search for Wild West, and the context of Wild West here is an individual trying to perform an adventurous activity. And on the left-hand side, you can see a keyword search returning a results, where based on the keyword West, a basketball image is presented, and then similarly a wild animal is presented as part of the return results. And on the semantic search, you can see that both the results are eventually pointing to a cowboy trying to ride a wild horse. And what that means is, again, under the hood, both of these different search types have different algorithms. Lexical search uses BM25 algorithm under the hood to provide you that relevancy score based on the search. And semantic search uses deep neural networks. We talk about some of the other different types of semantic search in a moment. So the advantage of doing a semantic search is it provides you more relevant results, and it understands the context and also enables you to perform a natural language query, and accordingly the results are provided. The disadvantage is it's going to be more complex. The trade-off is additional cost, and then you also need to eventually use an AI/ML model like embedding models to convert your input text into vector embeddings and store as part of your index, and then accordingly semantic search would be performed to provide you more relevant results. So as you can see, in the modern era of AI and ML and generative AI, vector search is a type of similarity search which is eventually used to find the documents or the data points that matches to the given input vectors. And vectors you can think of as an high-dimensional vector. So for example, in the context of, you use your fingerprint, where you have a fingerprint scan on your mobile phone, and based on your fingerprint scan, it automatically understands the pattern of your thumb, and accordingly it opens up. So it's eventually a numerical representation of your input text to find the semantic meaning of that particular word. And the main idea behind the vector search is, again, to represent your data like text, images, audio, video, or any other type to provide you that high-dimensional vector to find the relevant meaning of the given input text, and accordingly find the shortest possible distance within the vector space, and accordingly provide you the results. And KNN plugin within the OpenSearch enables you to do that. It's an algorithm, and there is two flavors of KNN plugin. One is K nearest neighbor, and other one is the approximate nearest neighbor. Again, there are pros and cons of using two different algorithms. And again, the idea is to kind of find the similar vectors to the given input vectors. As we have seen in the previous example of where a semantic search, where it captures and provides you the meaning, as I mentioned, you have to, again, convert your input text as part of the indexing stage to convert into vectors. Let's say, for example, you have a product description, product ID, and price, and all of the different columns as part of a data set. Then you have to decide which specific column you want to vectorize, and accordingly you have to plug in ML connectors to convert that into vector embeddings. Moving on to the second type of search is the hybrid search. So this is, again, fundamentally, which enables you to use a technique that allows you to combine both the lexical search and your semantic search. So under the hood, there's two different scores using two different algorithms as part of your search process, and accordingly the results are merged into, the scores are merged into one single score, where there is an, again, normalization process happens behind the scene, and accordingly the scores are calculated, a combined score of both these approaches, and then based on which the results are provided to you. The third type of search is the multi-modal search. So what that means is where you would eventually apply a mechanism of combining your text as well as images as part of the search capability, where you need to generate the embeddings for your text and the images, and accordingly it will enable you to perform the search. In the context of semantic search, hybrid search, multimodal search, Under the architecture adopter is a transformer encoder, which uses dense vectors, where for a given input text, it tries to convert to the corresponding vectors, and accordingly, the vectors are indexed to allow you to perform all of these 3 different types of search. And the 4th type of search is a sparse search, which enables you to combine the advantages of leveraging the deep neural networks. So what that means is, for the given input text, in the case of sparse, where there is a sparse encoding, which is a different encoder architecture, try to create a list of tokens for the given input text, and I accordingly finds a similarity or the meaning of that particular context, and accordingly the results are provided. So there are pros and cons of using dense vector compared to sparse vector, and there is a trade-off in terms of higher efficiency in terms of the resources, whether it's compute and memory, and there are other benefits in terms of the data structure used in the sparse encoding versus dense vector. So there is pros and cons for you to understand before you decide how your indexing strategy is going to be, how your partitioning strategy is going to be, and what kind of capability that you want to provide as part of your application, whether it is search for your product on your website, or the search is used for embedding with your GenAI applications. So depending on the use cases, you have to be selective where you want to start, whether you want to start with lexical search or with the ML-powered advanced search capabilities. Eventually, the challenge with, if you're not clear about which specific use cases or which specific search type you want to support, you're going to go back and forth in terms of re-indexing your data and then trying to vectorize your specific fields or columns. So it's going to be an iterative process. So be clear with your requirement and accordingly evolve your product on these search capabilities, because the cost, the effort, and the overall process of enabling your application with these capabilities are going to be evolving over a period of time. So let's try to kind of understand OpenSearch OR1 instances. How many of you heard OR1 instances in OpenSearch? Anyone using OR1 instances? No? Okay, that's good. So just wanted to understand, like, where do you get started, right? So OpenSearch in turn provides you the compute offering, an compute instance family offering, where you can eventually get started with general purpose, compute optimized, memory optimized, and storage optimized instances, similar to an EC2 instance family. So the challenge with those instances are pretty much where you have an hot storage attached to your primary instances, and then you accordingly perform your search. And to solve some of the indexing throughput as well as the overall cost of OpenSearch, OR1 instances was launched in November 2023. The idea behind OR1 instances is it enables you to perform your overall indexing throughput backed by Graviton instances. And this is one of the first class of instances optimized for OpenSearch. And we have re-architected the storage layer of the OR1 instances, where you can see that the diagram, there is a data node. So these data nodes, nothing but the compute family. Like in this case, it's OR1 instances. Each of these data node backed up by a compute storage, compute as well as the storage, the local storage, along with an a remote S3 storage as well. And in the diagram, you can see the yellow blocks. That is your Amazon EBS volume backed up by an S3, where as you index your data into the data node, which goes to your primary storage, which is EBS volume, and the data gets automatically synchronized to Amazon S3. This is called segmenting replication strategy, which was kind of completely a new design. And the data gets copied from the, and we typically recommend you to have at least one replica, and the data gets copied from your S3 towards the replica node instead of directly copying from your Amazon EBS volume, through which you increase your indexing throughput. So that's a benefit where you can see on the slide, the 80% of indexing throughput is improvised using OR1 instances. And also the cost, you can see 30% of reduction compared to other OpenSearch instance family, where it eliminates or it reduces the cost and it provides you the higher throughput. And again, one of the other advantages of using OR1 instances is natively it supports automatic recovery. What that means is where if you have a red indexes in your data node, as you can see the red block here, the data gets copied from Amazon S3 based on the specific indexes having an issue with that particular sharding. And it does automatically reading from S3 instead of from your primary storage to provide as much resource as possible towards your primary data node for the indexing throughput. So let's try to understand OpenSearch Serverless. How many of you are using OpenSearch Serverless? No? Okay. So the way OpenSearch Serverless architecture designed is completely different than the provision clusters, where we try to decouple the compute and the storage layer, with powering Amazon S3 as your storage layer. And due to this separation, where we can scale your indexing as well as the search, processing in terms of your queries coming in, where the gateway try to route, whether it is indexing request or the search request, where the compute and the storage scales dynamically without having any constraint to consider, whether if you have a huge volume of search requests coming in, where it can scale independently compared to your indexing request. And it supports 3 distinct collections. We call it as an engine within OpenSearch Serverless. To start with, the first one is the time series, where it helps you to perform the log analytics and other time series related use cases with a built-in storage tier of Amazon S3, which again eliminates some of the complexities around you to decide on the indexing and the sharding strategy. And the second type is the search, which enables you to perform full text search, keyword search, or lexical search, offers you automatic scaling out of some of the sharding replica, with your search types. The third type is the vector collection, which is pretty much the popular in the world of GenAI, where it acts as a vector engine or a vector database to enable you to quickly get started with your vector search use cases, where if you're trying to build a RAG-based architecture using Amazon Bedrock knowledge base, it automatically creates that vector within the OpenSearch Serverless collection type. So let's try to understand the tiered storage model within the OpenSearch. As you ingest the data into OpenSearch, your data gets stored into the data node, which is acting as your primary storage layer. And what you see here is the hot node. And hot node possibly provides you the highest throughput in terms of throughput as well as the performance in terms of indexing as well as searching new data. As you index the data gets copied towards your ultra-warm nodes, where instead of you having your primary storage like EBS volume in the hot node, you can migrate the data which is infrequently used, or probably you're not heavily relying on this huge volume of data sitting on your EBS volumes, which increase on the cost as well. So if you think that there are certain set of data which is not accessed infrequently, then probably that's where you can look at leveraging ultra-warm nodes. And ultra-warm nodes provides you a scenario where if you're not writing heavily on these indexes, and where you are trying to look at frequent queries on your hot data, and you want to offset some of the cost by leveraging the ultra-warm nodes, and ultra-warm nodes would able to do that. And as you perform the queries on the hot node as well as ultra-warm nodes, you can eventually decide what is your partitioning strategy on moving the data from hot nodes to ultra-warm nodes. And if there are certain scenarios where if you still think that there are certain set of data which is sitting on ultra-warm nodes are infrequently accessed, and you want to still further reduce the cost, then there is a possibility of moving those data from ultra-warm nodes to cold storage as well. The trade-off is that the data sitting in cold storage cannot be queried or written. So as long as you try to reverse that data back to ultra-warm node, then that data is queryable for you to perform the search capabilities. So you need to think of your long-term strategy on how you want to move this data to reduce the cost, also to have a better performance as well. And all these model of moving the data from hot node for your frequently accessed data and moving that to ultra warm node for infrequently accessed data, and similarly for cold storage as well, there is a feature called index state management within OpenSearch, which enables you to configure a management policy to move this data based on the time and the period that you want to retain this data within those specific storage tier. And you will see that in today's session, Pat will talk about how they have leveraged tiering storage mechanism to achieve the cost reduction as well as better performance as well. One of the common challenge in bringing the data to OpenSearch as you decide to leverage OpenSearch for some of your use cases, how do you kind of ingest the data? And typically we have seen customer get started with Logstash kind of a tool to self-manage it, hosting on infrastructure and trying to ingest the data. And eventually over a period of time, you'll see that the infrastructure management and the scalability of these tools becomes complex for your operational team to manage it. So it becomes a burden for your team. And that's where AWS tried to look at solving this problem in a managed service offering. And that's how we introduced Amazon OpenSearch Ingestion Service, which enables you to handle this complexity. And it's a serverless data collector that delivers a real-time log, metric, and traces into Amazon OpenSearch domain, that's provision clusters, as well as the serverless collections as well. And again, it's powered by Data Prepper, which is an open source data collection tool that offers you to perform filtering, transforming, and normalizing, and even aggregating the data in terms of the various downstream analysis and visualization as well. And the service integrates with pretty much heavily on most of the common data sources and sinks, like Kafka, HTTP sources, and OpenTelemetry collectors as well. And it offers 30 pre-built connectors for you to get started for your use cases where you can derive these insights from your data within no time. So this workflow talks about how typically the OpenSearch data ingestion pipeline works, and as I mentioned earlier, one of the common challenges, how do you bring in the data to your OpenSearch, right? And the way you get started is where you configure your client application, and this client application could be your application sitting on an EC2 or EKS or on-premises or anywhere else where you have a good connectivity towards AWS cloud. So you configure this application as a data source, and then it moves towards the next stage of buffer, where it's backed up by Amazon S3 as well as Amazon SQS, which actually takes those data and buffer as a persistent layer. And then the data moves towards the process layer, which is again a processing unit for you to apply various transformation tasks in terms of filtering, or maybe you want to kind of do some aggregation before that lands, the data lands into OpenSearch service. And this is backed up by, again, a managed service offering of Amazon OpenSearch Ingestion Service, where you will eventually have an endpoint for you to configure for your client to ingest this workflow or the process. And once the data lands into OpenSearch service, then you can eventually start applying your query patterns. And the data format here we're talking about is a JSON, where you use REST APIs with a JSON format to ingest from your client applications. And the way the service works in terms of scalability is where you eventually need to configure your minimum and the maximum OCUs for OpenSearch Ingestion Service. Accordingly, it scales. And again, the side note that you will see how Trellix have leveraged OpenSearch Ingestion Service, starting from a self-managed tool, and again, the complexity of building and managing the tool has burdened them, and they moved to ingestion pipeline to eliminate all of this heavy lifting. So one of the common challenges of a customer, where if they're seeing an exponential increase in the data to derive the business critical information or even operational insights from the data due to the various complexity of various pipelines and the processes and the tools that they have eventually developed or implemented over a period of time. And the zero ETL offering from Amazon OpenSearch Service eliminates that complexity in terms of the data integration process, enabling you to a seamless process of where you enable zero ETL for all of the services that you see on the left-hand side with a native integration to eliminate the complexity of managing those hundreds or thousands of data pipeline across different data sources to bring that data towards your OpenSearch service. And also you will see that we launched recently a feature within OpenSearch service called direct query. So what that means is you can query your data sitting in Amazon S3 or Amazon CloudWatch Logs or Amazon Security Lake for you to perform a query using SQL, OpenSearch SQL query, which enables you to provide you the insights directly without you building or creating your own set of tools to do that. And once the data lands into OpenSearch via Amazon OpenSearch ingestion service through zero ETL, then you can start again building your guardrails and the access control mechanism for you to say which specific user have what level of access on OpenSearch dashboards, as well as the access permission in terms of which specific queries can be executed on the data sets, considering you have critical data like PI data. And you can also eventually integrate OpenSearch with extended ML models as well, considering where you want to adopt a semantic search or advanced ML-powered search, then you need to leverage these embedding models, considering whether it is text, images, audios, or videos, where OpenSearch offers you a locally hosted or native capability of hosting these models, or even the custom models. But if you think you already have those models leveraged from Amazon Bedrock or SageMaker, then you can integrate OpenSearch with Bedrock and SageMaker or other, like again, we do support custom models, Cohere, Bedrock, and SageMaker through ML connectors. So ML connectors act as a plugin for you to leverage these models, whether you want to host it locally or in an external platform within AWS. And that's completely integratable. It's just a native integration where you need to enable this plugin, and then accordingly you can leverage these advanced configurations. And last but not the least, you can eventually use Amazon CloudWatch to really build an observability across various integration aspect of it to see the resource utilization as well as the query patterns that is coming towards OpenSearch. And you can use AWS CloudTrail as well to monitor the overall auditability of the API transactions. As OpenSearch works on the API in terms of your query request, then eventually you have to kind of have that understanding of which specific client or application trying to invoke these clusters. You have a QR code as well, which enables you to kind of deep dive on understanding how we have implemented this. Without no further ado, I would like to welcome Pat Lynch from Trellix to talk about Trellix journey in terms of how they have started from POC all the way towards production deployment. Thank you.
Hi folks, my name is Pat Lynch. I'm a senior software architect and principal engineer with Trellix. I've been with Trellix about 18 years, and my normal focus, I guess, is massive scale, high performance, and low cost. Actually, just before I continue, my 6-year-old asked me yesterday what I was doing today, and before I could answer, he said, "Are you just going to tell people about computers and how to use them?" I hope we'll get a bit more use out of this presentation than that, but we'll see. The QR code at the end, we can prove. So a little bit about Trellix, I guess, to start off, because I'm sure none of you have heard of Trellix. We're an award-winning company that was created after combining the expertise of McAfee Enterprise, which I'm sure many of you have heard, and FireEye, security companies with more than 37 years of industry experience and leadership. Our AI-powered open platform has more than 500 integrations across all security controls. We're trusted by over 53,000 customers, including 80% of the Fortune 100, and we protect more than 200 million customer endpoint nodes worldwide. A little bit about the products. At Trellix, we have an integrated platform for enterprise across endpoint, email, network, data, cloud, and security operations. We have industry-leading detection and response solutions. We have generative and predictive AI to power detections, guided investigations, summarization and threat landscape contextualization. And we have resiliency in architecture, management, and operations across on-premise, hybrid, and cloud. So XDR hot storage and searched here, and I haven't said anything about XDR yet, but that's basically extended detection and response, and that can unify threat prevention, detection, and response using data ingest from tools across the organization's security stack to correlate across multiple sources and to contextualize security alerts. So the XDR hot search and hot storage tier is what we'll focus on in this presentation. So looking at the existing workload and challenges, Elasticsearch was part of the critical infrastructure in XDR, providing the hot storage and search tier, which is central to customers' threat view. It was also used for the real-time threat hunting and automated detection framework. We ingest billions of events every hour across the clusters, and that at peak scales to about a couple of million events per second. Millions of searches are performed across the day across petabytes of data, and the expectation is always sub-second latency. We had thousands of expensive nodes across 33 self-managed clusters worldwide in 9 AWS regions. These all had onboard SSDs. And we had continued challenges of management and upgrade with self-managed clusters. And no matter what we did, any change we made had to incur zero downtime. So just looking at some of the existing query patterns, every day there was between 1.3 and 3.3 million queries per day handled. Of those, there was between 5,000 and 30,000 distinct query patterns being handled, which means they're pretty much ad hoc queries most of the day. 41% of queries look at data in the last 24 hours. 65% of queries look at data in the last 36 hours. So what did our next steps look like, and how could we improve on what we had? We had a few options here moving forward. We could tune or tweak the existing setup, but modernization was still required. We'd still have self-managed, and we'd still have something that was very expensive, and we'd love to get rid of self-managed. So we also had something that was already optimized. We had previous experience in optimizing a very similar cluster in EDR, where we managed to get 50x improvement in query performance and reduction in COGS, but it still needed modernizing, and it would still be expensive and still be self-managed. We did investigate some alternatives, not only OpenSearch. We looked at a few alternatives and did a full POC on one of the options, which we did use in EDR, and it was very successful in EDR. But when we looked at that use case for XDR, it didn't fit. It just didn't fit for the use case at all. So it kind of highlighted it's really, really important to validate the solution for each use case you have. So I guess why OpenSearch Service? It's managed service, meaning we can focus on adding value for the customer rather than focusing on infrastructure. Trellix has a great relationship and partnership with AWS, so it made sense to work with these guys. The ease of upgrade to latest OpenSearch service made this a no-brainer. An upgrade triggers a blue-green, meaning no impact at all to production. We could achieve reduction in operation costs and better support. And the OpenSearch ingestion pipeline, as Kanniah mentioned, it reduces data transfer costs and compression, and autoscales to handle spikes in ingestion load and takes technical debt off our plate. So I guess to summarize, managed OpenSearch looked like it would greatly simplify our hot storage tier. So what did we do? What did we find during our POC phase, and how did that impact the architecture? I guess just to give you some details on the methodology we usually use, we tested production scale and beyond. We disprove any of the documentation. We don't believe, documentation from AWS or anybody else. We prove and disprove it ourselves to make sure it'll fit for our use case. We cost model in detail, and we iteratively cost model based on the use case. Looking at some of the POC challenges, initial assumptions changed. Our initial POC predated the availability or the general availability of the OR1 nodes. We initially assumed we could use one replica, or actually in some cases no replicas, and quickly rely on the quick recovery from EBS in case of node outages. That turned out to be a little more complicated than we anticipated, so when OR1 became available, we actually jumped on that, and the cluster restoration with one node took 7 minutes, so we went with one replica, as Kanniah highlighted, and that basically meant no outage at all. We still needed multiple shards for reliability. The solution was modification, indexing and sharding strategies. We added additional replicas. We changed the lifecycle policies on certain indices to try and get consistent shard sizing across the cluster. We did run into a number of shards per node limitations in ultra-warm large nodes. So the solution was changed from ultra-warm large to ultra-warm medium and spread the number of shards across more but smaller nodes. And we had scaling issues around our own self-managed ingestion pipeline. So the solution here was to use the OpenSearch ingestion pipeline, which basically scaled throughout the day as our ingestion changed. So some of the architectural decisions, we merged multiple clusters in each region. There really wasn't any need to have the split we had after migrating to OpenSearch cluster. We experimented with various indexing options. We finalized on per customer indexes for improved flexibility and visibility. We'll likely change that to merge some of the smaller indices into shared indexes instead. We utilized OpenSearch ingestion pipelines. We deprecated our custom indexing, which got rid of a lot of technical debt. We now handle varying size workloads throughout the day, auto-scaling to meet the needs. We embraced OR1 instances, as Kanniah mentioned, giving the spoiler. We're now getting improvements in indexing throughput, a more cost-effective auto-recoverable component, backed by S3, and we implemented ultra-warm storage. I mentioned earlier about the percentage split across 24-hour kind of query and the 36-hour query. So we have between 1 day and 36 hours in hot storage, and the remaining in ultra-warm storage, which actually reduces our costs significantly. Just looking at the architecture, it's exceptionally simple. Data lands in S3 after it's been processed and decorated, and that actually is the jump-off point for it to go into our archive search storage, but also into our index search storage, which is where OpenSearch comes in. We have SQS and SNS kicking off then, which basically starts off the ingestion pipeline, which lands the data in the relevant shard for the customer. I guess what the migration process looked like. We took a safety-first step to our approach to migration. As I mentioned, these clusters were part of critical infrastructure. They're central to customers' threat view. We actually took one of the busiest clusters in XDR, and we ingested both Elasticsearch and OpenSearch at the same time. And as we watched the production load and how our cluster actually behaved while ingesting data, we tweaked, we tuned, we stabilized the cluster with the help of the AWS OpenSearch team. We replayed production queries against the new cluster to verify results and to check the latencies. And we then merged more and more of the Elasticsearch clusters in those regions into that single OpenSearch cluster. And as we got more comfortable, we rolled the solution out across all regions. Looking at the timeline. So how long did the entire process take start to finish? We started actually our initial discussions around August 2023 with AWS, with a POC started off in anger, I guess, in 2023, with the POC completing in 2024. The production shadowing for that one big cluster, the biggest cluster, I guess, was completed in April 2024. And the migration, the full production migration started in May 24 and was fully switched over by July 2024, where all the Elasticsearch clusters were shut down as well. So that was around 10 months, I guess, start to finish, which given our safety-first methodology and the criticality of the project, we're very happy with the outcome. So I guess the part a lot of you have been waiting for, what were the outcomes that Trellix found? We reduced the number of deployments. We went from 33 self-managed deployments to 9 managed OpenSearch deployments. We replaced our custom index service with OpenSearch ingestion pipeline, so that's managed service, and ingested data can be sent in compressed format, saving us money. We used the OpenSearch index state management policies, which basically meant we could deprecate our own custom lifecycle policies. And we used the OR1 instances, which reduced cost and increased durability. And we added additional monitoring using OpenSearch dashboards and Amazon CloudWatch. From a COGS reduction point of view, we merged the 33 clusters to 9 OpenSearch deployments. We compressed data during ingestion, so that gave us efficiency in COGS. And we transitioned to the OR1 instances, which, as I mentioned earlier, gave us improvements in indexing throughput and a more cost-effective auto-recoverable component backed by S3. And we implemented the ultra-warm storage split, as Kanniah kind of highlighted. We got cheaper storage layer backed by S3 for the majority of our data. Sorry, I'm just going to grab some water. So from a performance and COGS perspective, we improved indexing performance by 40%. Operational indexing issues were reduced by 90%. COGS savings achieved, including RIs, was about 35%. Without RIs, it was about 28%. And the COGS savings achieved overall was about $3 million. In summary, I guess, this was an SRE-driven migration effort with the help of Dev and QA. They did an amazing job. And thank you so much to the AWS team who were with us from the start right to the finish, making sure this was a complete success. I would say it's critical to test at scale, at production scale and beyond. We successfully migrated 33 self-managed clusters to 9 managed OpenSearch deployments. The timeline was about 10 months start to finish, which again, we're very happy with given the criticality. We made significant COGS reductions, approximately 3 million, and some operational enhancements made as well. I guess next steps, as you probably heard Kanniah say, we have barely scratched the surface of what Kanniah talked to earlier. I'm looking forward to using some of the AI-related features that actually are available, and also using OpenSearch Serverless for some different use cases. But also, I need to look at some of the query performance for data and ultra-warm nodes, just to improve the performance there, and also look at changing from per-tenant indices to merging some of those smaller indices as well. Again, I guess, Kanniah, thank you so much, and folks, thank you so much for your time. Appreciate it.
Thank you so much. If you have any questions, we'll be around. Please feel free to pop in and ask any questions. Thank you so much.